It's a pleasure to introduce as the first speaker of today's colloquium Oliver Porth from the Anton Pannekoek Institute at the University of Amsterdam. He's an assistant professor there since October 2018. Before that, he was a postdoc at the University of Leeds and Goethe University in Frankfurt, where he started some of his work on the theory side of event horizon telescope interpretation of that image. And his primary interest is dynamics of astrophysical plasmas, and that's what he will tell us about today.
Yeah, excellent. Great. That's exactly right. I'm very happy to be here. I'm happy that you are as well. Yeah, I want to talk about a couple of things that we think are like transient phenomena in black hole accretion. So we have seen lots of observations of flaring behavior and some intermittency. Now we are at the stage where general relativistic magnetohydrodynamics is like giving us a good broad brush picture of what happens on average, how to launch a jet. But I think the next things that we have to understand is how to also explain like when things flare and what could be the dynamical mechanisms behind that. So I will talk about flux tubes, plasmoids, and transient jets in this context. Right, first I want to have two slides just on talking about accretion variability, what is actually understood and what do we want to model. So what is the challenge actually for the theorist here? I have two mechanisms that are very, very different also in the regime that I think they operate, so they probably will not. They explain some features of what we observe, but none of these mechanisms that I'm going to talk about can explain all the observations, for example, of the galactic center. So we're quite far away from like having, like, say, this is the model because it explains all of the observations. But I just want to give us some ideas what can happen in close to a black hole in an accretion flow. Right. So accretion variability and flares, just as an overview. So the focus here is the galactic center. The galactic center has variability on many time scales, and also it has variability in different frequency bands, which are like somewhat different. So if you just start at the sub-millimeter, so that's what the EHT sees, and has been monitored also just for many, many years. We have a slowly bubbling variability. Flux increases by like 40% from time to time, and it's all quite moderate, and it's not really something that we would call flares. So, and this is actually quite well understood, this regime. We had a large code comparison effort where we actually can model quite well like what this bubbling accretion flow is doing, and everybody kind of agrees with these kind of levels of variability and also the power spectrum and all of these things. It gets quite much more interesting if you go to higher frequency. So if you go to the infrared, for example, the galactic center is doing roughly 4 times per day. It's actually flaring up by a factor of 10 or so in flux increase, and you have like 4 per day of this.
And so it cannot be stars, unresolved stars.
I think now this is quite excluded, that you have this like 10, 30 flux increases in stars. I think so. I have a slide where we actually resolve this close to the galactic center, even astrometrically. So at least many flares are definitely not from X stars. It's even more extreme if you go to X-ray, so you have also daily flares, and the energetics that you need to explain these flares are like 5 times 10 to the 37 ergs, so this number will come up later when we are trying to compare to some models. So an X-ray flare looks like this in different wave bands by Chandra, so it goes up, and the whole thing takes around 8 kiloseconds or 1,000 seconds. We have substructure in all of this that of course indicates there is the size of the emitting region might be as small as a few gravitational radii. So if you have substructure by like 40 seconds, that means like your emitting region is really small. It must be like 2 RG or so. So this gives us some indication that things are happening close to the black hole when this flux goes up.
How do we know it's not X-ray binaries?
How do we know it's not X-ray binaries?
We don't.
Well, this kind of levels of 10 to the 37 erg, like fluxing.
Do X-ray binaries at that?
No, that is very typical X-ray binary flux.
Yeah.
Yeah, but the thing is, it's right superposed on Sagittarius.
Within an arc second.
Within an arc second.
Arc second is a big
Arc
piece
second
of
is a parsec.
Yeah, so you could have an X-ray binary there.
we could have an X-ray binary, but there's also like flares that are like coincident with submillimeter and infrared.
Okay.
And yeah, and all of these, but not all of them are correlated, but they are examples.
The ones that are correlated with infrared are definitely not X-ray binaries.
Yeah.
And the other argument against X-ray binaries, in answer to Avi, is that 2-3 arc seconds away, Chandra would resolve them, and they're not seen.
Yeah.
No, but within 1 parsec you could have a lot.
Hide a lot.
Could have a lot, because you have a million stars.
Yes, no, of course you can. But
You can have a million stars. You have a million
Yeah.
stars there, so out of a million stars, definitely you can have an X-ray binary.
Yeah. So they're correlated.
I mean, if there were, X-ray bursts, you would instantly recognize them. There are none very close.
Okay.
But anyway, there
Yeah.
are lots of other issues.
Great. So next thing, so that one observation that was actually quite interesting 1.5 years ago, this so-called gravity flare, where the gravity is an infrared interferometer that has a resolution that's also like on the level of EHT, so 20 micro-arc seconds to 70 micro-arc seconds, and so it can really resolve stuff close to the event horizon. And what it saw was actually astrometrically resolved like a blob of plasma that was flaring up in the infrared for around an hour, and it basically fulfilled a full circle around the black hole on a radius of 6 to 10 Rg. So this is also quite some good coincidence that this is actually happening really in the accretion flow. So there were essentially three observations that basically were consistent with like the orientation that is inferred from this. This means we're looking, if this is actually correct, this observation, we're looking like maybe at an opening angle of 30 degrees into the galactic center on top of the disk, for example. Second thing that's interesting about this is, and it's also puzzling if you look at polarization, this thing makes basically also in 60 minutes it makes a full loop in polarization. And that's something that's actually not so easy to understand in terms of like a normal accretion flow. Because in an accretion disk, you actually basically shear up all the magnetic field, you have a differentially rotating flow, and the magnetic field is all toroidal. So if you have a field which is toroidal, and you have an accretion disk,
Use the green one.
just to illustrate this point, why this is like maybe a challenge to the model. So if the field is like also in phi direction, and the blob is moving around the disk for some reason, some emission blob, that's what we do. The polarization, it looks exactly the same after 180 degrees. So this is really hard to get around with this kind of models. Yet the observation showed like a same periodicity.
And sorry, could part of the field be coming from an outflow, not just the disk? Completely different orientation?
It could be coming from an outflow, yeah, if you're looking right into it. But the simplest go-to model would be kind of this thing. So in the first thing, in the first part of the talk, I'm trying to explain like how to make such a field that actually is not toroidal. But actually, what was been found when you orient the field like sticking out of the disk, and you incorporate like gravitational lensing in your radiation transport, then you can actually find configurations where you perform only a single loop. And this is, yeah, it's a bit hard to explain because you need to incorporate that the light bends and the polarization is then transported in a particular way that allows you to make a single loop. But the big ingredient that you do is you have a colloidal magnetic field. And yeah, how to do this? How to make a colloidal magnetic field in an accretion flow? It's kind of what we then call so-called flux tubes. We're going to talk about a little bit what their properties are, because we're seeing actually these kind of field configurations in simulations. So we just thought, okay, they need these fields, we have this in the simulation, so what are the properties? And for this we have to turn to so-called magnetically arrested disks. I think in this institute, I think many people are familiar with the type of accretion flows that we have in the galactic center or in M87 modeling, and this MAD type is when you have very strong fields. So this dynamics is then quite different from the same type where we have this nice bubbling variability.
Do we have a good reason why this would be better than same?
So there are two reasons. One is a good reason to look at MAD. For example, if you look at the structure, this was also with Michael Janssen, the structure of the polarization, increasing the baseline, you see that actually you need a fairly large-scale field in order to explain the polarization signature. So this points towards that actually these fairly large-scale fields that feature here might be present in galactic center. There are other reasons to think that actually these MADs might not be so good because they might have too little variability because of this larger scale structure. So there's another paper pointing out that they're not variable enough. So there's not a single model that actually can fit all the bills, as I've said in the introduction. But it's interesting to just investigate like what happens dynamically in such type of flows, and then we can maybe zoom in later and rule one of them out. So we do simulation with the black hole accretion code. That's the code I wrote with many collaborators. But when I was in Frankfurt, it's called BUG, and you can actually fully download this as an adaptive measure refinement GMHC codes, reasonably fancy, and you can just start similar simulations if you wanted to. So this is actually how the simulations then look like. I'm just directly showing you a movie. Let's see. That would be here. And now I've lost my mouse. Okay. Oh, wrong window. I'm sorry. Okay. The action happens anyways later. So this is density in a meridional plane. This is the so-called magnetization. We have strong fields. There's always this funnel region of the strongest fields. So this is green. Here is equatorial plane, density, and sigma again. So this is a type of flow that a MAD does. And as you can see here already, there's some kind of eruptions happening very close to the black hole. You get from time to time these kind of light blue regions that kind of come out of the black hole. That means you have low density plasma erupted out of the black hole. And what this then does actually, if you look at it in the accretion disk, you have these low density, so the log scale, so the factor of 10 to 100 lower density than the ambient medium, and then these blobs start to orbit around the black hole. And this is of course quite suggestive. You have these kind of flux bundles that actually sustain for quite some time their structure and go around the black hole. And if you look at what they actually look like, this is what I showed mentioned to Ramesh before. Yes, we can trace field lines. What they look like, they look very different to a typical disk field. So a typical disk field is this like yellow field lines. This is completely like dominated by the toroidal component. They give you this 180 degrees flip of polarization. And yet these flux bundles, they are actually field lines that were before rooted at the black hole. So they have these very low densities. They kind of come out of the funnel region. And yet they have this like field topology that kind of sticks out of the disk. So this is of course something that, we think, maybe this is what's going on in the gravity flare field with this polarization. But let's do like a little bit more analysis. So what do these flux tubes typically do? I've seen it in the movie. They kind of come out, they orbit. So how often do they orbit? And how do they come out in the first place? So a cartoon picture that you could be drawing, and it's also quite an interesting possibility. A MAD accretion disk, the magnetic flux in the MAD is very strong. The magnetic field really wants to come straight out of the black hole. And when you have these straight field lines coming out of the black hole, it actually pinches the flow here quite significantly. You get an equatorial current sheet. And what can happen in this equatorial current sheet is that these field lines can in principle come together, and then they can reconnect. And when you have reconnection, it's kind of always rings a bell that also there might be non-thermal particle acceleration going on. And then this reconnected field line might actually escape the black hole, and there's lots of tension here, so it actually wants to escape fast. And then you have this like field line that was before in the black hole, so it has this different colloidal dominance, and then it's orbiting around. So what did they do? We track them. We see.
Your simulations are MHD, you said.
Yes.
So you don't have reconnection, do you?
We have numerical reconnection, and we are doing right now resistive MHD simulations.
But what we are looking at, the images, do they have reconnection in?
Well, there is actually a change of topology in the field lines in the simulations. Because of numerical, and Bart will actually next month come here and tell you like what happens if you actually include resistivity and really resolve the current sheets and allow for a more consistent way of doing this. But this is already a first look like what potentially happens. So, right, so let's go through this quickly. So what do? We track them to some extent. They actually escape rather fast from the black hole. They go out and then they actually orbit around here. So this is this kind of like tension making them expand from the black hole, and then they kind of orbit around the magnetospheric radius, these flux bands. They can orbit for like, you can find them for 1 or 2 orbits. So this is phi, so going around once more. So they can survive actually quite some time in the accretion flow. This is of course important if you want to like have a blob that kind of does not shear out because of differential rotation, like while it's on its orbit. And they are able to survive for quite some time with periods of 200 seconds, 200 M, 2000 M. So we also looked at the energetics. So if you want to explain this 10 to the 38 flare, 37 erg flare, you need to have the right amount of energy in these flux bundles. So here's the statistics of flux bundles. So they are at all different sizes. This is the size statistics, and this is the energy statistics. So they peak at around 10 to 38 ergs. So if you were to dissipate this amount of energy, you would have enough to actually like make an X-ray, an infrared flare. And you can find actually energetic flares at all sizes. So you have even like small radius, highly energetic regions, small flux tubes that have like this, the right temporal variability perhaps. Okay, so this is just an outlook like what we're seeing. We are doing more statistics now, and yeah, also have to look at the cooling time of this. So the cooling time of this gravity flare is around 15 minutes. So and if you have just one-shot acceleration like here, like when the flux tube basically comes out and is loaded with relativistic particles, that's of course the picture. And then it might emit non-thermally, this for infrared. And in 15 minutes, that's kind of 1/4 of an hour. So you might get around without re-acceleration, but we have to do a little bit more analysis here. So second part, and I still have some minutes left, is another type of transient phenomena. It's like a very different regime, and these are actually formation of plasmoids in accretion flows. So the motivation for this is that the galactic center, it's not so obvious that it has jet. There's a remark of the argument made that whenever the galactic center flares in the X-ray, it's coming right up onto this X-ray radio correlation. So, right, so we get this kind of correlation, and this is what jets do in other galaxies. So whenever we have a flare, that might also point towards, okay, now galactic center maybe has started a jet. So how can we make these kind of jets be temporary and transient? So this was motivated by a study of Parfait, Janssen, Borodov, where they actually studied like small-scale magnetic fields, making actually transient jet phenomena. So this was led by Antonius Nathanael, and we extended the study in that sense that we now actually take into account the full magnetorotation and stability of the disk, and not just advect like different polarity loops. We seed, this is a very simple setup, we seed the field, the accretion disk with different coherence, length of fields. The difference here in the blue, red, and the red is just the fact that in the red loops, basically there's essentially like a current sheet here, potential current sheet has a polarity inversion in flips, and here it does not. So actually there will be quite some dynamical differences between these two types of simulations. And again, we use a bug code to do that at fairly high resolutions because we really want to like resolve these plasmoids forming in the accretion disk. Right, so the first thing that you look at, so these are all the models. This is the sigma parameter. This is a simulation that looks very similar to what we have seen. This is also what we have in the code comparison. This is a high sigma funnel, and then you have the accretion flow. Model B is very similar, so it had small-scale loops, but somehow they reconnected to make a big loop. I think this is also mostly understood. And then you have also this funnel C and D, where you actually have these small-scale loops. They keep the small coherence length in the field in the disk. And then once in a while, such a small loop will actually get to the black hole, get enough magnetization out, and give you like a transient jet. So whenever number is high, you can actually launch a Blanford-Snide jet. So these small-scale loops actually manage from time to time to squeeze out a jet. This is just zoom in. And then another one will come in and the jet will shut off. So this, of course, somewhat suggestive of like how to make a transient jet. This might be a way to do it.
Is it like
Oliver, what was the spin?
0.9375, always the same.
How efficient are these transient jets?
They are very inefficient. I will show this. So this is the energy efficiency. This is a typical sane simulation, 1% efficiency or so. And the transient jet, yes, it is around 10 to the 3 times less efficient. But from time to time, such a transient jet has enough magnetization to actually get something that's on the level of a sane type outflow. So 1% of the accretion outflow is then in a very short amount of time put out in the jet. And in the galaxy center, this might actually be enough. So,
Is it similar to coronal mass ejections in the sun?
well, not really. So there you slowly twist the field lines, I believe, and then you get the like buildup of stress and quite like flaring reconnection. Here it's more that it's more of a like impulsive acceleration of the Blanford-Snide process. You have strong enough fields, and then they will, and it's kind of governed by whatever field comes in, how long this can last. So yeah, it's a little bit dissimilar, I would say. Okay, right. So they are very fluctuating. So this is good, highly variable, but very, very different from this type of jets. But on average, very low power, of course. But we might have some ways to actually tweak that. Another thing that is interesting here is to look at the current distribution. So there's lots of current sheets and like potential sites of magnetic dissipation happening. Model C and D, if you just visually inspect this current, you see that they do very different things. They have all these small scale, all these little loops here, and these little loops are actually magnetic islands, so closed magnetic field lines, actually O points that come basically out of reconnection. So since you have these small coherence length fields here, you have many more of them here. And the nice thing about these loops is that they actually trap particles, relativistic particles, and then you can attract them and do all sorts of modeling things with them. So just changing like the orientation of these loops from here to here makes quite a big difference in like, your overall result as far as plasmoids are concerned. Some of them do more interesting things. Some of them actually make it all the way to the black hole. So these field lines, previous loops that you seeded, and then you have here a loop field line coming out of the black hole, another one at the other end. This goes in, this one comes out, and now between them you make a current sheet just in the black hole magnetosphere. So, and in this current sheet you can have a nice chain of all of these plasmoids. This is quite interesting because like in the black hole magnetosphere you don't have this turbulent flow that like pushes your plasmoid around in all different directions. But here actually this plasmoid is then like flying out with a typical Blanford-Snide jet that you can also launch at the same time. What you also find is that these plasmoids, they are outward moving when actually the magnetic field that's coming in has enough magnetization, and you can convert enough magnetic field to heat, and then they become hydrodynamically unbound. And in that case, they actually fly towards the observer and keep their relativistic particles that are trapped in them, at least in 2D they are trapped. And yeah, might be giving rise to some kind of flares. So we track them just to get a little bit of an idea what's happening with them. You can follow their orbits actually, so they kind of go around at 10 Schwarzschild radii or so, and then like expand along with the flow. So this is of course another way to kind of have a circular orbit around a black hole, as Richard actually mentioned. This thing would actually be happening in the jet, and this is what would be actually
Where they're observed in microquasars, you see these plasmoids.
Yeah, this is also the star-disk interface, right, where this happens. So yeah, in a black hole you can't have like this. Yeah, well, yeah, you can. well, okay, you mean these
Microquasars.
these
they see this
superluminal
plasma.
things
Yeah,
coming
exactly.
out, yeah. I
Exactly.
don't know, yeah, if that's really plasmoids or shocks.
Well, it could be your
It could be, yeah. This could of course be many things. But yeah, so okay, just to send like what are the future steps, so we actually can track all these plasmoids now. On the interesting ones, we can really follow what is the typical magnetic field. We can now put this in the spectral modeling. We have the path, and then the next thing is actually to see if this is any way doing something that a flare would be doing. But yeah, in principle, all of this comes out of the simulations nowadays. Okay, just a little outlook. I also wanted to talk about resistivity, because that reconnection, the process that we invoke that makes this particle heating and acceleration, needs really a resistivity prescription. But the question is, what is the correct resistivity to take is completely unknown. I mean, it's definitely, it's not collisional, so you cannot put your Spitzer resistivity in. You have to kind of find a good way to motivate the resistivity, and the project that we're doing right now is actually comparing, like in a simple local box, at very high resolution, 60,000 squared cells, MHD simulations, to particle and cell simulations to actually calibrate the Ohm's law resistivity, which we can then in principle bring back to the global simulations, such that you actually get the right electric fields coming out of the current sheets and get the right particle acceleration, electric fields. So this is the next ongoing project. Bart will show in a month actually with a uniform resistivity that this picture of plasmoids also survives, and that, yeah, you will also show about the mad current sheet, I believe. Yeah. The next step is actually to use the calibrated resistivity. We really say something about like the observational parameters. Okay, these are my conclusions. I think they're a bit dense, so we'll not go through them. Basically, I showed you two mechanisms to make that we see in simulations that might be responsible for transient phenomena in black hole accretion. They're quite different in different regimes. So mad accretion has strong magnetic fields. And you have this erupting flux bundle, has weak magnetic field. You have an MRI turbulence, lots of small-scale reconnection, and basically plasmoid formation. Eventually going outwards when they are strongly magnetized. Right, and this is actually all I wanted to, yeah, you have more to say?
I just thought a bit more about the initial conditions of those four models. And I think, like you say here, that you need those small scale fields. But I think, looking at my resistive simulations, you see plasmoids copiously forming everywhere, both in the sheath and in the disk, with also a global.
It might be a resolution thing, but I think it's
saw
somewhat plausible that, like, when you allow the fields to make a big loop, that's the first thing that will happen. Then basically they won't have time to really to back to the black hole with a small coherence length, so that you can have this repolarization going on. But yeah, might be resolution issue, but we went already quite far in resolution as well.
But you had, so I would suggest you had very high resolution for the Model D, but not for Model A and B. So
we
I
have
think
a model, we have, okay, let's talk about this later. We have not done Model A also with 4 times higher resolution too. Yeah. Okay, let's
suggest we take the speaker for 3 minutes.
So Oliver, this erupting flux bundle picture for the flare that gravity saw, that's very attractive. But if I understand the dynamic, the picture there, the field lines pinch off through reconnection. Then this field line snaps out to a large radius because it's trying to straighten up, and then it orbits around the black hole, right?
That's the general
idea there. Yeah. Now gravity, in this scenario, gravity has seen that orbiting part. Should gravity have seen this radial outward acceleration, and did they see it?
They did not see this, so they saw just the basically, yeah, it's just start. Well, I don't know. You could play with your orientation angle such that this kind of it's a bit outward moving, so it comes from here and goes here. But I wouldn't say so. I think this is all consistent with being a circle. I think. Yeah.
Right. So it would be nice to know what is the time scale for this shooting out.
In principle,
should also be the same. There may be a 2 pi for the orbit, but other than that, it's going to be the same order of magnitude.
If it shoots out quite fast, then when you shoot out, you don't see it yet because maybe you didn't look, or it just developed, triggered, and then.
Right. Since they saw 3 of these things, it may be interesting to check whether.
Interesting to check the conjecture.
Yeah.
Right.
Yeah, but it's a nice picture.
Is the 50-minute orbit a prediction that's compared to the result?
This is a prediction, with a vertical magnetic field, playing with the orientation angle and the position of the blobs a lot. I think Jason Dexter came up with this, really thinking about lensing and really how to make the polarized radiative transfer do a single loop. It's not entirely obvious to draw, but these are GRT predictions.
Yeah, but I think Peter is asking about the 50 minutes.
That's what you're
In
saying.
your simulation, it was 20 Rg, right? This is 6 to 10 Rg.
Yeah, but we have I have periodicities from 200 to 1000 m. So 1 hour is 180 m. So we kind
The
of
orbital time is correct. 50 minutes at 6 to 10. That's correct.
That's correct, but the
For you,
question
it was
is what.
slower.
Well, I have a range, right? That's why I have many
you can
things.
get
So
it.
it goes from 200 to 1000. So this is
Since
the
the
range.
200 is closer to.
That's closer,
Okay.
yeah. But the big ones are too slow. The
Too
really
slow.
nice ones are too slow.
So these flux tubes, would they also be something that we can observe with the EHT?
So 2 things. So I did just a normal ray tracing in of these simulations, just to also get a scaling for the energetics. And if you just put a thermal EHT, if you sub-millimeter emitting particles or the thermal ones, these flux tubes have a rather low density, so they are actually not dominating the sub-millimeter flux in this model. So once you load them with relativistic particles, yes, potentially they could also show up in the EHT band. But this is a step that is right uncertain at the moment, what is the acceleration of this? Otherwise, it's not the normal thermal emission that the EHT sees, like thermosynchrotron,
Okay. Oliver is staying for the rest of the afternoon and also tomorrow if you wanted to talk more with him. But we have to move on, so let's
Second speaker today is Michael Janssen. Michael is a last year PhD student at Radboud University, and he's an important contributor to the Event Horizon Telescope, developing the fringe fitting codes for the EHT and simulating the physically motivated process of obtaining data in VLBI, and this is the subject of the talk today.
Okay. Thank you. Thank you, Maciek, for the introduction. I'm happy to be here and happy to talk to you about simulating VLBI observation with special applications to the Event Horizon Telescope. So I'll talk about actually how we are able to simulate entire observations, so how we are able to actually emulate all of the different effects that are present in the real observational EHT data with our simulations, and also why we want to do this, because as probably know, so the EHT already has observation results. So we have first image of a black hole shadow. So I'll try to explain to you why it is still useful to work with simulated observations, even though we already have the observational data. So one way to think about synthetic observations is that there is a simple way to turn such a model like this, is, for example, a model that Oliver describes, a from ray-traced GMHC simulation. So it's synthetic observation. We have a way to take these theoretical models as they come out of the computer, as observed from, as they would have been observed by a perfect instrument, perfect sensitivity, perfect resolution, and turn them into synthetic observation so to say if this would be the reality of what actually goes on in the direct vicinity of a black hole, how would the EHT as an imaging instrument observe this reality?
What is the BHC?
What is
The
BHC?
black hole cam.
Black hole cam. That's a project from the ERC, so it's a European partner of the Event Horizon Telescope. Collaboration. So the PIs are Luciano Rezzolla, Heino Farke, and Michael Kramer. And today I will talk about one specific synthetic data generation pipeline. It's called Simba, that I've developed together with a fellow PhD student at Radboud University. But this is just one of the several synthetic data generation pipelines that we have in the EHT. And the basic idea of Simba is to try to process synthetic data in the same way as the real observational data passes through the entire EHT system. So this is an overview of the code of Simba. What's important is actually only here these red arrows over here, so they indicate the flow of the synthetic data through the entire pipeline. The other steps are here. There's some optional steps or some steps that deal with the metadata of an observation. For example, in a real observation you have metadata from the telescopes, such as some temperatures that describe the noise in the system that we use then to calibrate the real data. And in the same way in the synthetic pipeline we also generate synthetic system temperatures that we then also use to calibrate the synthetic data. So we start with the source model as the one I've shown on the first slide, and give some information about the arrays, so where the telescopes are located, what are their sensitivities, and at what time do they observe the source, and what is the weather, for example, like at each station. Then we use the Max Silhouette software that's developed in South Africa by the group of Roger Dean, that basically takes this input information over here and turns it into an observation. So it's not very complicated, so you do Fourier transform of your source model, since the EHT is an interferometer, and then you add all of the corruptions, so the noise that you get from the instrument, the effects from the atmosphere, and so on. The idea is that Max Silhouette generates a synthetic data set that should look closely to what the real EHT produces from the correlator. So the correlated EHT data is something that we try to reproduce here with Max Silhouette. So then we take this still corrupted data that had all these effects that we're not able to correct for before correlation, then pass it through the entire EHT calibration machinery. So we take this synthetic data that is corrupted and calibrated pretty much in the same way as we also deal with the real observational data. And then the last step is that we use some image reconstruction methods. So we have, to this code, we have coupled the script, the imaging script from the EHT imaging software was developed here by Andrew Chair. And this script is actually the same script, the same software that was used to generate the EHT imaging image of a black hole from the real observational data. So we take the same scripts, the same method to then reconstruct a source model from this synthetic data. So in that way, we want to know, so when we start with this perfect source model, how accurately are we able to reconstruct this source model, and what features from the source model do we still see after the image reconstruction, after it passed through this entire thing. Now, why do we want to do this? There are many reasons why you want to work with synthetic simulated data, and I've highlighted here a few of them. One is, for example, that you can use synthetic data to better understand your data and your entire instrument. For example, you can put in some polarization leakage terms, so those are errors at the telescopes. Let them pass through the entire pipeline flow to see how they affect your data and your results, and how accurately you would be able to correct for those effects. Another use case is, for example, imaging parameter surveys. So when we reconstruct images with our software in the EHT, we have some free parameters that we need to set, and you can use synthetic data set with known ground truth images to, in a machine learning type of fashion, to solve for these parameters, so that you have the optimal parameters, you have optimal image reconstructions from your known synthetic data, and only then use the software to reconstruct an image from the real data. Next point is that you can use the software to understand what type of science you can do with your instrument. So you can, for example, ask the question based on synthetic data where you have some jet with some different types of flux densities. Are you actually able to reconstruct or to detect this jet in the final step of the pipeline of the image reconstruction? Or are we sensitive to the spin of a black hole? And probably more for the future would be interesting if we're actually in some point sensitive to alternative theories of gravity that would predict a different metric than the standard Kerr metric, for example. I think the most important use case of synthetic data is more on an operational side of things. For example, in the EHT we have every observing window. We have only a few days where we can trigger observations, and we have limited resources. And the question is, how bad can the weather get before you should no longer trigger for an observation? So we can run many synthetic data sets in different weather conditions, and then see at what point is the weather getting so bad that we can no longer extract any science out of this observation. So that then tells us at what point should we trigger for an observation given the real weather conditions and the real observation. And next, lastly, of course, with the development towards an expanded EHT array, the NG-EHT, you can use synthetic observations to identify the optimal locations for future stations, and also how sensitive these stations have to be useful. So today I'll show just a few examples related to these things I've highlighted here. So some of the scientific prospects that we can identify with synthetic data, and one example of how different weather conditions can affect your data. So I had a few slides on describing GMHD simulations as our typical input model for these synthetic observations, since GMHD basically, those models describe our best understanding of what's actually going on. I guess I can be really quick after the talk from Oliver. So I can probably, this was the general idea, what you have to do when you solve GMHD equations, to basically just solve for the flow of magnetized plasma in a GR space-time. And typically, the simulations look like this. So you have an accretion disk with some magnetic field. You develop instabilities, and self-consistently, when you have a rotating black hole, you launch these jets. Within the EHT, we have certain libraries of these simulations where, for example, the spin is varied or the magnetic field configuration.
By the way, in quasars, only 10% have jets.
Quasars.
So you said that most typically, but it's actually the other way around. Typically, you don't see jets.
Oh, I see. Yeah, I was talking, just about the simulations.
I know that Heino likes jets, but in reality, it's 90% without jets.
I see. Okay. Yeah, I'm not paid to say that there are jets everywhere, but I'm allowed to. Right. So the next step is then, of course, as you all know, right, the GMHC simulation that just trace the dynamics, so we need to compute the radiation. There's this nice animation that shows what you have to do in this ray tracing code. So you solve for the geodesics of these light rays. This simulation, for example, nicely illustrates how relevant for the EHT, how when you have a black hole shadow and you have some light that's come from the back, how then on Earth, on the faraway receiver, faraway telescope, you see this enlarged dark region, the black hole shadow. But when you do this ray tracing, you get a few or additional parameters that you can vary over, for example, the inclination of the source or the description of the temperature of the electrons, because in the GMHC simulations themselves, we only trace the temperature of the heavier protons. This, for example, then what this library looks like with some different geomet ray trace GMHD simulations. Now come to the more detailed, the gory details about how we have these models. What are the exact steps that we're taking in our pipeline to turn these models into a synthetic observation? The first one is very simple. So we take Fourier transform of an input model. The next one is that we need to simulate the atmosphere of the Earth, which is quite tricky. So one thing, for example, we do is that we take weather parameters from the VLBI monitor, for example, which is a service that we use also for real EHT observations to log the weather data at all the different sites, and also to have predictions for future for weather forecast, basically. And when you add the atmosphere, you have additional attenuation of the signal, but also you have additional noise, because at 1 millimeter the atmosphere also emits. You get phase turbulence in your signal, and you get additional delays, so differences in arrival times from the signals to your different stations. Then we need to simulate the effect of our instruments from the telescopes. So the first thing that we need to simulate is our pointing offset, so when telescopes are not perfectly pointed, or just simply when you have atmospheric seeing, so when your source is moving in and out of the telescope beam, so you lose some signal. In that way, you have thermal noise because from the instrument and from the fact that you're quantizing your signal. And every station has a certain, it's never perfectly calibrated, so you have some gain errors and some polarization leakage. Then the next step is to do the calibration. So we have, again, within DHT, we have multiple calibration pipelines. For Simba, we've coupled, because it was basically based on software compatibility, we've coupled the pipeline that I've written that's based on the CASA software, and that on its own is a very complicated thing. It does many things. So we've coupled this calibration pipeline to the synthetic data generation chain. And what the pipeline does is then to solve, for example, these atmospheric effects in the same way in the synthetic data as it does when we let it run on the real EHT data. And the last step is we use, again, the EHT imaging software. We also use it for some additional parts of the calibration. But the most important part that we use it for is to reconstruct the source model from this data. So from this input model, after I pass to all of these additional steps, we use the fiducial EHT imaging script that was developed for imaging of MIT7 to reconstruct a source model from this data. So then there are a few things you can do with the synthetic data. One is, for example, you can look at different GMHD models that have different values of spin. This is a high negative spin, zero spin, high positive spin. And then you can ask the question, just with a simple image reconstruction, what do these models then look like as if they were observed by the EHT? What you see is that for the 2017 observations, so what we see in the image is pretty much really dominated by the photon ring, which is present in all of these models. So the good news is that all of these models compare quite good to the observational data, but the bad news is that with a simple image reconstruction, you cannot really tell them apart in this way.
So how much better would it get if your point spread function just got like a half an hour? Would you be able to tell the difference between these, maybe?
So if you mean by point spread function, like the individual beams,
what you'd be convoluting.
I see. So when we have more higher resolution,
yeah.
Then so with the EHT, it's pretty difficult. So in the end, I have one slide where I show what we would see in 2020.
Mm-hmm.
But if you go that route, really what you want to work with is actually space VLBI, where you get these very long baselines, and then you get really sharp image reconstructions. But I don't know out of my head if some lupus space we had these specific spin models. Right. But of course, this doesn't mean that it is impossible for us right now with the current EHT to say anything about the spin. All of this is saying that just with simple image reconstruction of taking the observation from a full day, turning that into one single image, with that method you cannot say something about the spin. So if you want to say something about the spin, for example, what you probably want to look at is some features that are in time domains, so time variability features.
Actually, how far?
No, I'm looking at the top, and that is the best you can hope with an infinite resolution, put another station on the moon, whatever. And I have a hard time telling.
Right. Right.
What are we talking about? What's the difference?
Right. Yeah. So it's also a problem here. Those are just snapshots. So again, with the spin here, it's very difficult.
Is
So
the orbital time very different? So if you have a hotspot, it will be because obviously the ISCO is on top of the black hole for a high spin, right? So.
Well, it is different for different modes of the spin, but then the question is, does the emission actually, most of the emission does actually come from that close?
Yeah, because that's where the radiative efficiency is the highest, right?
Yeah.
At the ISCO. So perhaps the time it takes to go around
Right.
is the best indicator, rather.
Right.
And then you don't need a high resolution. Just look at the hotspot.
Right. Right.
That's it.
Yeah, so probably actually it's something that I think Maciek wants to work on, right? Because you can see if you have some variations of where actually the brightest spot is.
When we wrote it 12 years ago with Avery Broad.
But you won't know the radius of it will be high depending on the radius of the thing that's going around.
No, because
right? If it's at the ISCO, you know that, but in general it could be.
Well, first you know the mass of the black hole, and you see the size of this ring, okay, where the emission comes from, and then you measure the time it takes a hotspot to go around, and then. So the time it takes to orbit depends on A. Depends on the mass and A.
Oh, you mean if you could also resolve the radius of the orbiting?
You do resolve here.
Well, not very well. You can't. How far are you from being able to see that ring there?
Sorry.
The photon ring.
Oh, he sees it.
Yeah, we do.
I don't think you see that. I think if you subtract that ring from the top, the image is unchanged below. That ring is only about 10% of the luminosity.
I'm not sure if that's true, but something
to. There's no claim in the literature that ring has been resolved.
No, resolved not. No.
Well, that was what I was asking.
But you can
okay. No, yeah, we cannot resolve this ring perfectly.
Right.
So that's true.
But how far are you from that?
I wouldn't know off the top of my head.
And you wrote a paper on that with us.
No, I didn't. I'm just a theorist. I said what it should look like, but I haven't, because some people have been going around making statements that it could already be seen on the HT tour, but that it could already be seen in the current data. I don't know what the situation. So I'm interested in your opinion on what.
Okay. Well, if you mean on really resolving this ring, then no, not with the current data, and also not with I think with any observations on the ground. I think that's impossible, even if we go to slightly higher frequencies. If it would be possible with space VLBI, probably, but I would have to check.
I think I guess you're right. So the flux is dominated by the lensed emission from the accretion disk. I think that's what we agree on in the theory working group, because this is an infinitely thin structure, so it has lots of intensity but little flux. So if you don't resolve it, it does really not make the ring. But
it's not just the accretion disk, right? It's also the counter jet.
Yeah, but I mean, the most of the intensity comes from the not from the ring. I think this is understood. So that's what you're saying as well. Yeah.
Oh, I see. So the integrated intensity is.
Yeah.
Well, it's an optical illusion, which I was suffering under as Ramesh knows. It looks to me like that ring is most, especially like on the right one, it looks like it's almost all of the integrated luminosity, but even in that one, it's only like 10-15%. And you would,
Okay.
From these observed images, we could try to estimate what fraction of the particles are emitting at the observed frequency, but in order to do that, we'd actually need to deduce the filling factor, or what the real volume that's actually contributes to the images. And can we do that from the simulations? Do you think you can get a good idea of volumetrically what fraction of is contributing to the observed flux? Because then you can just estimate the partial pressure from, let's say, relativistic synchrotron radiating electrons computing at the observed frequency from the cooling time, from the luminosity, over that actual volume. So do you think you can actually take these simulations, compare them with the observations, and understand like what the real filling factor of the real emitting regions are?
I would say yes, but
It's
yeah,
a
Oliver
figure
is-
in paper 5, right?
yeah.
There's a figure in paper 5.
So you actually got the filling factors.
Well, we show the origin of the photons, like bin locations, and then like in the r theta plane. So you can call this a filling factor, yes.
So like, what do you like 10 to the minus 3?
I don't know the number. It's a figure.
So figure 5. Look for
Okay, paper 5.
Yeah. Paper.
Yeah. Okay. One other thing you can check, for example, you can look at models that were published before the observation and after the fact, check how these compares again with the simple just image reconstruction, how they compare to the observational data. Right, again, it's hard from this to tell a big difference between these models given the current resolution and sensitivity from the EHT observation. But again, the good news is that they kind of compare well with the observation
of the mass.
Right. Do you know which mass they assumed in these two papers? I guess they assumed the high mass. Right. I would assume different. They have one other example of a more recently developed model that was developed by Jordi Davila. So what most of the standard GMHC simulation that we've worked with so far, at least within the EHT collaboration, they assume that the electrons have distribution function that is given just by relativistic thermal distribution function, so there are no effects of accelerated particles that you could get from shocks or magnetic reconnection, for example. So what Jordi did is he took a certain one of his GMHD models, and then just only in the ray tracing and computing the emission, he added some electron acceleration to electron acceleration effects. And the model is shown here. So this is the standard model, so we're just with the thermal distribution. So here, for example, one thing you see in this particular model is you have the footprint of the jet shown here as foreground emission is quite bright. So that's really a distinctive feature in this model. And then when you include the accelerated particles over here, what you get is a little bit more flux here in the more extended emission region, actually from the jet. And these are just the same. These two models convolve with the 10 micro-arcsecond beam. And then we checked, again, we led it through the whole pipeline and did image reconstructions based on these two models. So that's shown here for the configuration of the 2017 array. And these are now really the image reconstruction models. So those are basically the models that are computed by these image reconstruction softwares before convolving them with the resolution beam. And you can see that actually here with the 2017 array, we don't really see any of these features. So there's no real emission to be seen here, and also there's no real emission to be seen from the jet. Then when we go to future observations, so that will actually happen soon in 2020. So we have new additional stations for the Greenland Telescope, Kitt Peak, and Noema. You get a very nice boost in mostly sensitivity. Then you see actually here in this image reconstruction some of this foreground flux actually being picked up, and you can see it over here, and also with the model where you have somewhat extended jet emission, also the reconstruction. If you squint your eyes and believe hard enough, you could maybe say that maybe here, this may be the jet. So you can see maybe this is going in an
or
interesting
could it be the beam pattern?
direction.
I mean, the beam pattern also can elongate some of these images.
They can, yes, but the EHT beam for M87 is quite it's quite symmetrical. So
I mean, on these, on the images that are in the newspapers, you can kind of see like there's elliptical.
So one other study that we did is, so we wanted to understand the effect that really bad weather can have on our observation, because for the 2017 observation we were really lucky and it was really good weather across most sites. So we made one simulation that included just overall bad weather by putting in high opacity attenuation, short coherence time, and slightly worse in focus solutions from the telescopes. And then we varied one parameter, which is the pointing offsets from each telescope. So that means that overall telescopes are always slightly mispointed, so flying a little bit blind with your telescopes with respect to the source. And the other effect is that on short timescales you also have some variations that could be caused by atmospheric seeing or by just a telescope moving when there's a lot of wind, for example. And then we increase uniformly across the array. We add these larger and larger growing pointing offsets to see how bad do the image reconstructions get. And you see that at some point really the pointing gets so bad that you lose actually a lot of data, so the signal becomes too weak to get any detections on many baselines. To actually the biggest stations, those are the ones that drop out first in these, because they have the most narrow beam in this type of simulations. So those type of parameter studies, they can be interesting to identify really at what point does the weather get so bad that it's no longer worth it to trigger an observation, because the science return from the data would be minimal.
So this pointing, is this because of weather or just mechanical problem in the telescope?
So in the current code we have a very, very simple model to do it. It's just you have one Gaussian beam, and then you have a source that is offset. And this number, it does multiple effects. So how we simulate the pointing is, first of all, we say that telescope operator repoints the telescope every few scans. So every few scans we draw a random number, distribution driven by this mean. And then the telescope is off point a little bit, and then every few scans it deteriorates more and more, and then repointing, and we draw again. So that is on the long time scales. At the same time, on the short time scales, we have some ad hoc way to say, okay, there are also some variations, a little bit smaller than this, that occur on the coherence time. So by that we say, whenever you have a very short coherence time, it also probably means that your atmospheric seeing is bad. So you have the same way that the source is moving a little bit in and out of the beam on very short time scales.
But this must be very rare. I mean, like a hurricane passing by or something.
Yes, yeah. Well,
So messages don't observe during a hurricane.
yeah.
Tropical storm is okay.
Well, there are actually some cases in where we have some telescopes that can have some difficulty pointing in certain conditions. For example, when just after sunset, when the dish is still warm and you wouldn't have a good thermal model of your telescope, you can have some relatively bad pointing solutions, and then these type of effects that can actually be present, or they are actually present in the data. So this is my last slide, just a summary of a few of the things that I was talking about. So I focus on the Simba pipeline. Actually, to my knowledge, is a very elaborate VLBI synthetic data generator. So as far as I know, I don't think that there are any other public software packages out there that try to combine all of these different effects and put them together in a single pipeline, which is why I think that this is a very useful tool to use for multiple things. So what I've shown is that in 2020, well again, this was you squint your eye, and based on just one very particular model, maybe should be a little bit phrased more carefully, but towards future observations we may actually be able to see something that could resemble the footprint of the jet in M87 with our observations. Same time, again, you have to, was just based on one single model, but you probably want to explore again larger parameter space with all different kinds of models. But this shows some prospects that we may be able to measure the electron distribution function, or say something about the electron distribution function with our observations maybe in the future. And then towards the NGEHT, I think synthetic data will become very important to identify where future locations will be, and for the next science goals of the EHT, synthetic data is very useful to look for or understand time variability in the data, and maybe towards the future also see if we would become sensitive to some non-GR metrics. And if you're interested in the software, it's public, you can get it from here. It's also Dockerized, so it runs on every system. Docker containers are here. And the paper was accepted by ANA, and I think it should be published soon. Thank you.
Questions?
Very briefly, could you tell us about the blue sites in this picture?
The blue, let's see, so what are the
What is the
color
time
codes?
scale that we are thinking of?
All right, so yellow is now, orange is 2020. All right, yeah, blues are all potential future sites. I think actually this plot wasn't generated here. I think this was part of the NGHT
well, I can
press
tell you
release.
very quickly. So many of them are just suggestions, but overall is going to join on this guy.
Yeah.
Haystack there is an active project of evaluating what are the chances of getting the dish in Massachusetts.
How can you observe 230 gigahertz in Massachusetts?
Well, on a cold winter day,
when there is no hurricane.
so, you know, this is an ongoing investigation if this actually is possible.
The
But
snow is an issue.
Okay. Okay, I see.
Baja.
And Bolivia? Or BOL, whatever that is?
I think this is more of a suggestion
My
of what
brain.
we would like to have on the unless maybe, Michael, you know about Bolivian dish that would...
And VLT.
I'll say just a little
Oh,
bit.
great. We have an expert, Jonathan.
Well, I don't know if I'm an expert. The first thing to say is that true submillimeter sites, places like Mauna Kea and Atacama, and even where LNT is in Mexico, Sierra Negra, they're incredibly rare. And we're kind of scraping the bottom of the barrel already. I mean, there's a very nice site in Greenland, a Greenland telescope. It was going to go to the sort of the summit of the polar ice cap, but it has funding issues and it's very expensive to deploy there. It has worse weather than the South Pole. The answer is that there's actually a list of about 30 sites, far more than is even on this table, and there's an active program to deploy water vapor radiometers and weather monitoring equipment, very inexpensive home-designed weather monitoring equipment. And Alex Raymond, who actually isn't here today, has built something with a student, and we're going to rationally survey it's a scattershot approach, a large number of sites.
Why is Australia not included? What do you have against Australia?
So Australia has no. It's interesting. It has no high topography, right? But it is very dry.
It's a good site for radio telescopes.
It's good for 1 millimeter radio telescopes. You need incredibly low precipitable water vapor, which you typically find on high mountain peaks. And Australia's, extremely flat. There might be a little bit of it that it may not be all that good from a position on the UV plane perspective. Well, although it's a little bit hard to
because
judge.
the location of Australia geographically it has a small overlap with other stations apart from South Pole.
It's not too bad.
This Indonesia.
Depending on the source as well.
You are missing the
The sites that are shown on this map typically provide there's a great deal of interest in intermediate length baselines, right? The EHT is sort of focused on very long baselines, but to link the ring to the jet, you've got to image very high angular resolutions simultaneously with more coarse resolution. And so for example, the sites in Africa are designed to link the existing sites in Europe to the South Pole, because the baselines from Europe to South Pole are very long, and so they're very high angular resolution, and so placing something in the middle. I think this particular map is a marketing document that went with a press release, and it's got a few guesstimates of where we might place things. But the answer is that there's a very in-depth study being done of far more sites, and most of them are going to be discounted, and these might be amongst them.
But you should market the truth.
Really? Sorry. What world are you living in?
No. Yeah, that's right. Good.
Right,
excellent point.
Any more questions?
I think this map there was a press release for the NG at EHD on the CFA website, and I think that's where this map comes from.
Comes from one of the white papers that we have written, but of course that is before this study of the sites in details is made.
Yeah.
Any more questions?
And actually, well, I don't want to keep talking, but the haystack, it's a terrible place for the
I was thinking,
right? It's absolutely awful,
Yeah.
right? Except in winter it can be dry, right? And we do our observations in March, which is sort of winter. But the point about haystack is there's already an observatory there. There are already EHT collaborators.
Yeah.
They have a 37-meter dish, which has an improved surface due to a recent upgrade. And so it's incredibly low-hanging fruit.
It's like looking under them.
Although we may end up, paying a price because we may get nothing out of it. So it's being looked at, but it's by no means a 1 millimeter site. The hope is that if you have a 37-meter dish and bad weather, the two will compensate, right? The large collecting area will offset. Okay, so there you go.
Right. Do we have any more questions to Michael? If not, let's then thank Michael again.